Calculating acceleration. Let's take a look at the difference between acceleration and average acceleration with an example. When we draw an acceleration graph, the line that we draw, the straight line that we draw, goes through all the data points. With this type of movement, we expect a straight line graph. However, in reality, when we actually collect data, very rarely will all the data points be exactly lined up in a straight line like they are on this graph. So we take the average acceleration. What that means is that if some of the data points aren't exactly lined up, we can still draw a straight line graph showing the trend. So this is more like the type of data you would collect in an experiment. And we draw a line that represents the average acceleration, noting the points that don't fall exactly on the line. They still show a trend. When we do experiments in the lab or in real life, very rarely will you get perfect data such as in this graph. So we have to take the average data and draw a graph that shows average acceleration in this case. Let's take a look at slope on a velocity versus time graph. On the y-axis we have velocity north in meters per second. On the x-axis we have time in seconds. On this velocity time graph, we start with an origin of 0. And we're not putting it right at the bottom, and you'll see why in a minute. I'm not going to put any numbers on here, but you should know that anything below 0 is negative, and then everything above 0 is positive. So suppose that an object is traveling north. Okay, and what we see here is a positive slope. And what it represents is the average acceleration north. It basically shows that speed is increasing at a constant rate. This would be like you're in a car, it's not moving at all at 0 at the origin, and it begins to speed up, but it's speeding up at a very constant rate. If you were riding in the car, you wouldn't notice any jerky movements, but you would be aware that you're speeding up. So the acceleration is positive, and it's also constant. Let's say you reach the speed limit and you continue traveling north. How would you show that on the graph? Well, it should be shown as a straight line. Okay. The velocity stays the same, whatever that is. Maybe it's 50 kilometers per hour, and you're continuing to travel north. Okay, so here we should make a note that the object travels north, and in this case at a constant speed. Okay, so let's say the object continues to travel north, but it begins to decrease its speed at a constant rate. How would that look? Should be a straight line graph. Okay, and in this case the acceleration, the average acceleration north is constant and negative. So it decreases its speed at a constant rate while traveling north. The acceleration is negative, but the velocity would still be positive because it's still going north. Okay, so basically it's traveling north and it's slowing down. When it reaches this line 0, what that means is that it's come to a stop, because if you look over on the y-axis, velocity of 0 basically means that you're not moving. Now if this line continues down past 0 or past the origin, the velocity is shown as negative velocity, right? We're below zero. But what does that mean? What that means is that we're increasing speed at a constant rate, but we're traveling south. And if we're increasing the velocity, that means that we are accelerating. It's a straight line, so it has to be at a constant rate. And because it's below the zero or below the origin, okay, it means that we are traveling south. And so we have an acceleration that is constant and negative. And again, it's negative because we're traveling south. And that basically is why the velocity is also negative. Okay, so how would that look? Okay, this part here just kind of gives you a summary of all the things I've written on the graph, but what would that actually look like? Okay, let's say that in the interval A, if you look back up at the graph, interval A was this part here, where we have that acceleration north. We'll call this interval B, where we have that constant rate. Interval C is going to be the time period where we're actually slowing down and returning to zero, and then interval D here is going to show that we actually changed directions and we ended up going south. Okay, so if we were to kind of map that out, we could say, okay, we started over here at home, accelerated, to a tree. This would be time interval A. And when we reached the tree, we basically kept going at a constant rate. So we reached our cruising rate, and then maybe we slowed down. So this would be negative acceleration or deceleration. And then we reached some goal, like we maybe got to a particular sign, and we turned around and started heading back. And this would be like D on the graph, where we're returning, or we're actually moving south. Remember, in each of these cases, we're traveling in a northerly direction. Okay, and turn around and we move south. So you could think about this graph as kind of showing a run where we start running at zero and we accelerate until we reach a speed that we're comfortable at. At B, we're just continuing at our comfortable rate and we're going for a nice jog, and then we begin to slow down, turn around, and then begin accelerating in the opposite direction. And we should make a note that we are accelerating here. Okay, so how can you calculate acceleration without a graph? Well, on a velocity time graph, you probably already figured out that the line on the graph is acceleration. So it's nice if you have a graph, because you can visually see the acceleration on that line. You can tell if it's a greater rate of change of velocity or a lower rate of change of velocity. Something like this with a steeper slope would mean that the change in velocity is occurring more quickly. Something like this would show us that the change of velocity is occurring more slowly. But we don't always have a graph, so it's important to be able to calculate. If we did have a graph, we could use slope. We could say, okay, well, the slope is just the rise over the run. But sometimes we don't have a graph, but we do have the change in velocity and time. And if we have those two, you'll know that the rise on any one of these graphs is velocity and the run is time. So really, to calculate acceleration, it's velocity divided by time. And we can use this formula as is if we need to calculate acceleration. We can also use it if we need to calculate velocity. Okay, we just have to shift some things around. This one helps us calculate velocity. Can also use it to calculate time if we're given the average velocity and the average acceleration. So we want to try some of the problems in the workbook and in the textbook so that you can practice using these formulas. Okay, one more thing we want to talk about, which is gravity. Gravity is the force that pulls downward on every object, pulls down towards the earth. And when we throw an object up into the air, it's still being pulled back to the earth, and that's why it falls back to the earth. As a matter of fact, the minute that we throw it up into the air, let's say we throw a ball up into the air, it actually begins to slow down. So initially it's moving fairly fast, and let's say this is the distance it travels in one time interval, like a tenth of a second or a second, and then let's say in the next time interval it doesn't travel quite as far because gravity's pulling it down, still 1 second, but it didn't go as far. Then in the next time interval it goes even less distance and less distance with each passing time interval, and basically slows right down, and for a momentary second as it's changing direction, not even a second, but for just a very split second, it kind of pauses and it heads back again. And then the whole thing is reversed because now gravity is stronger than the push upward on the ball, and very slowly it begins to speed up again, and you get acceleration downward. Okay, so we have acceleration in both cases. We have acceleration as the ball is moving up, and we have acceleration as the ball is moving down. It's just that upward, as it's moving up, the velocity decreases, and so it's negative acceleration. Okay, and then as the object returns, strangely enough, it's moving back down to the earth, but we still call it negative acceleration. And why is this? Well, whenever it's acceleration due to gravity, it's negative. And we can see why. Up is positive, down is negative, negative acceleration. So we can calculate acceleration due to gravity, but we're not going to do that right now. It's kind of a value that you have to remember. It's just 9.8 meters per second squared, and often whenever you have an object falling due to gravity, you would actually have this value, and actually we use negative 9.8 meters per second squared because if it's falling, it's moving downward, it's moving toward the more negative value. Okay, and that minus sign shows us that gravity pulls down. Gravity never pushes up, it always pulls down. Okay, so we'll try the problems in the workbook and then also try some problems from the textbook. This chapter, this section is really, really important to do lots and lots of problems and get a feel for this, the math behind this section.